Hello and welcome to Tattva Deep, conversations and explorations. For a fifth episode on physics, we sat down with Dr. Ashna Sen. Dr. Sen has double majored in physics and mathematics from Mount Holyoke College, USA, and thereafter obtained an MSc in Geophysics from Stanford University, UK. She works as an advisor and teacher at the Mayel Lyang Academy in Kalimpong, India, where she trains teachers to reimagine what mathematics is and how it can be taught. This is also the goal of her second book, Reimagining Mathematics, which was published in 2021. Her first book, The Rusted Trunk, is a historical memoir on the lives of civil servants of Bengal during the pre-partition era, and it came out in 2011. Dr. Sen was a first guest on Tattva Deep. She's both a mathematician and a physicist. In the first appearance, she helped me understand the beauty of mathematics and the importance of creativity, imagination, and intuition to understand it better. Our conversation on physics was equally engaging, where we discussed what physics is about, some of the big questions that physics is asking and answering, how humanities can inspire scientists, the interconnectedness of things, what makes it difficult for some scientists to give up long-held beliefs, and also consciousness. Welcome, Ashna. Welcome once again to Tattva Deep.
Thank you so much, Disha. Always a pleasure to talk to you and to see you.
Thank you, Ashna. I mean, the first episode of Tattva Deep was with you. And yeah, it was such a brilliant experience for me. And we've had so far one of the largest number of views on that episode. I think somewhere it's resonated with people on some level. So, that's great. So I hope with the physics, just we'll flow freely like we did for maths, and let's see how it goes.
Yes, yeah. I mean, that's the hope, but always a great pleasure to interact with you. And you really open up my mind in so many directions. So I feel very grateful for that opportunity. Thank you, Tattva Deep.
So I think the first question, let's start with really the most basic things about the subject. So what is physics?
Yes, I mean, of course, that's a very large question that physicists and mathematicians have been debating over for a very long time. But I suppose if you put it ask a simple question of how and what, whatever answers those questions, I suppose that's the quest of physics. So physics attempts to answer the question of why something is happening, why a certain phenomena is happening, or how it's happening. So if you have, the famous Newtonian apple falling from the tree, why is it falling downwards? That's a why question. If you have, a ball rolling down a slope, how is that ball, moving in that manner? So that's a how question. And this applies to things at the macro level, at the very micro and subatomic level. Of course, I'm jumping quite ahead. But these questions are attempted, I think, by the community in general. And of course, one standard way of looking at it is that physics also looks at, observes. Observation is a very big word in physics, and measurement, of course. So if you can measure and replicate and observe, then we are supposedly in the right track. Having said that, I feel the whole realm of physics and what it encompasses is also in a state of flux. It's constantly changing. So that which cannot be replicated might also be in the realm of physics, and it might also be in the realm of philosophy, for example. And there's a lot of interaction, I think, between other areas, both of science and in general of life. Life's big questions, big philosophical questions, sometimes within the ambit of physics and vice versa. So I suppose in general, this is what physics is certainly to me. But it's a very big question that probably is outside the scope of what I myself would understand.
Yeah.
What really is a physics phenomena. But
yeah,
yes.
but when I've been talking to physicists for a while now, and this seems to be how most of them are explaining it. From here, there seems to be some kind of a branching out, but there seems to also be an agreement on things like why and how, observation, the role of observation. And then, of course, a lot of them, as I'm sure we get deeper into the conversation, we'll bring up concepts like imagination, intuition. So these things seem to be found commonly among physicists, like perhaps the tools that they employ in order to achieve what they want to achieve through physics. So the other part which you said, which is some of the bigger questions, which is where I think a lot of general public find their way into the subject. So some of the big questions that physics is answering, and we also end up borrowing a lot of metaphors from physics. And we spoke to one philosopher of physics, Dr. Tim Maudlin, and he says that you have to be careful with how you deal with these metaphors, because it might mean something to you, while in physics it could completely mean something else. But apparently it still happens. Metaphors, right. Seep into public consciousness. Somehow it happens. And then these big questions, like you were saying, I don't know how many questions I've already asked you, but what I'm trying to get to is like, what would you say are some of the biggest questions that physicists have asked, and in what way would you say that those questions in seeping into the public consciousness have shaped the way the collective behaves, reacts, and yeah.
Yes, maybe we can step back a little to also addressing what is physics, because I feel we hadn't fully completed this.
Okay.
And this will also trickle into what you're asking now, what the big questions are. Before that, I mean, physics is a catch-all phrase for a very, multifaceted discipline. We can't even call it one discipline because it's certainly modern physics is super specialized. So I suppose roughly you can subdivide it into 3 different realms. There's classical physics, what we call Newtonian physics. There's, and that's a whole realm. I suppose it's the realm of the macro, what we see, the laws of motion, a kind of Newtonian thinking that's based on Galilean thinking, and a kind of Descartesian framework. That's one realm of physics. Then there's quantum mechanics, which is another rough, very broad area, very important area. And then, of course, we also have relativity. But within these ambits, my area might, myself, I suppose I'm in between mathematics and physics, and certainly I'm not a practicing scientist, but once upon a time, I delved into both physics and mathematics, and I was straddling the fence between, these 2 subjects. My area was fluid dynamics and fluid mechanics, and the science and the physics of flows, whether it's flows within the human body. So of course it encompasses biology. So it could be a question like, how does what is the mathematical nature of blood flow within the human body? When it's encased by, within our veins, which is a kind of compliant surface, mathematically speaking. So it responds viscoelastically to the flow, and this back and forth interaction is a very mathematically interesting phenomenon. So it's a marriage between maths right here. There are some people who study other areas of physics, certainly calculus, which was also invented, by or rediscovered by Newton,
Yes.
and co-discovered by Leibniz.
Right.
And previously, there's been, other cultures that have hinted on, been on the kind of periphery of calculus. So that's also something that brings in a lot of mathematics to physics and enlivens it. There's the area of optics, and optics, you might say, leads on to waves, etc., and all this, the wave phenomena, and light and how that behaves. And then suddenly we have quantum mechanics, which is its own entity, and that whole realm. So I suppose what you're asking is that what are the big questions that scientists and physicists have asked? Famously, they tend to be, the famous physicists tend to be the theoretical ones, I suppose, like Einstein and Feynman, Stephen Hawking. They get center stage. Right. But of course, there's all these other realms of physics that's also happening as phenomena, and people are asking these sub questions all the time. There's an area of physics that I had delved into briefly called plasma physics, which also asks the question of what is the background of the universe. So the universe is not as empty as we think. We used to think it was just pure vacuum out there. But as it turns out, there's, it's filled with plasma, not to be confused with the plasma of blood, but particles, separated by distance. Okay. Yes, so these questions of how and why, these very big questions tend to trickle into what is not my area at all, right. Quantum mechanics and relativity, the nature of matter itself, the standard model of matter, for example. So these are the big questions. What are we made of? What is matter fundamentally? Where did we come from? And various theories, whether it's the Big Bang, and I'm jumping, of course, in leaps and bounds, going straight to the Big Bang, but that's where the matter was presumably cooked. And what is this matter? What are the particles that comprise us and everything around us? It seems so far, with the standard model of physics, there's about 12 particles and 3 types of forces, right. the strong force, weak force, gravitational forces, and the Higgs boson giving everything matter. This is our general standard model, and that's how we understand the nature of matter. Right. But this is not all, because the standard model, I think, has some problems, and maybe some of your guests who are practicing physicists will be able to shed a lot of light on why the standard model also can be problematic. Right. So we think up something, and a lot of the experiments seem to help us along and corroborate everything until they don't, and then we revisit everything. So these big questions are constantly being addressed, but also, we are free to question that is physics the only channel of addressing these large questions? The nature of reality. Why should physics be the only vocabulary for it, or the only language for it, or even mathematics? What is reality? So then it comes into different layers, right. of the word itself. Right. Yeah. Right. And you have also had a lot of influence from the teachings of Mr. Jittu Krishnamurti. So what would be interesting to know is this, that you can start right at the beginning, how you first ever heard, how you first heard about him, if you got to interact, or your first impressions. And then how much did you keep up with what he was teaching, or how much did you stay in touch with his teachings, so that you think that they probably did influence your approach to math and physics both? Yeah. That's a very beautiful question, albeit a personal one. So if it's not too rude to start with a personal journey,
that's what I'd like.
That.
Yeah.
Yes, excellent. Okay. So just a few lines about Jiddu Krishnamurti, the great philosopher and thinker, who was born in Madanapalle, I think in 1895 or thereabouts. And he grew up in South India, and he was adopted by Annie Besant and incorporated or invited into the Theosophical Society, and hoisted, I suppose, as a world teacher and the coming Messiah. But at the age of 27, he disbanded all of this, and he gave that famous speech of truth is a pathless land, and thereafter he started giving talks all over the world about everything, I think. I mean, about the nature of beauty, what is what is true inquiry, very, very large questions, very beautiful questions, but very fundamental questions. What is death? What is dying? What is thinking? What is the nature of thought? Is thought a material process? So there were, I mean, it's a huge body of work, all his talks delivered over decades. So where I suppose I come in, he has been a huge influence on me, because my father was very, very interested in Jiddu Krishnamurti's teachings. And in fact, in the 1980s, he invited Krishnaji to Calcutta for the Calcutta talks, which was, I think, the only time Krishnaji, visited Calcutta, and it was still a very polluted city. So I do understand why he wished to visit, a second time. But jokes aside, it was a very popular talk. He gave a talk addressing 5,000 people, and I attended that. I must have been 9 or around thereabouts. It was very, very impactful, although I didn't understand anything at all.
Yeah.
In fact, I was slightly resentful because my father was spending so much time, after his long hours in the office, reading Krishnamurti, sometimes reading it out to me, and asking these big questions from a very early age. The nature of reality.
Wow.
I suppose very large questions that I felt at that time trickled into the realm of science, which was probably not his intention at all. He was not addressing these questions as to a scientist necessarily at all. But I felt that, he's asking these very big questions that perhaps science might address quite neatly or attempt to. So there was this kind of very early hope that I would be able to understand the nature of things, just the world around me. And I became more and more interested in that, thanks to Krishnaji, and thanks to this very early influence. And then I think with the passage of time, shortly after that, I started noticing my father was playing these VHS tapes, of interactions between the physicist David Bohm and Krishnaji.
Right.
And David Bohm was also asking questions that are otherwise very quantum mechanical in nature. And because he had first heard Krishnamurti asking these questions, like, is the observer the observed? And David Bohm saw it from a physicist's eye, and he was very interested in the questions Krishnamurti was asking, particularly about the nature of time, about the nature of the observer, about the nature of awareness. What is awareness? So these, again, these very fundamental questions of the nature of reality, whatever reality is, and certainly being able to hold these thoughts without jumping to conclusions very quickly, because we have no neat and clean answer. you see. So this interaction, watching these tapes, and eventually going to the States and reading a lot of Krishnamurti's books and David Bohm's books and trying to see what they were saying without really having reached the physics level at that time. I was an undergraduate, so I was scrambling and trying to learn all sorts of courses, electromagnetism, a course on quantum mechanics here and there, a little bit of plasma physics, a little bit of elasticity theory, maths thrown in. So I was trying to kind of gather all that together, but also somehow fuse it with what these philosophers were discussing. So there was that huge influence, but I think that influence also made me highly indisciplined, and as a scientist, as a physicist. And I'll say that is a very good thing. The reason I say indisciplined is that I allowed myself to ask all sorts of questions in the realms outside what was allowed, I suppose, in standard physics, or didn't show up in standard physics. Questions like, of course, this is the nature of matter, and we've seen so many particles, it's proven that a whole lot of particles have been discovered, at CERN and various particle accelerators. I even did some internships at Brookhaven National Lab and nearly lived inside a cyclotron or nearabouts. So I was doing all that, but I was actually asking the question, also questioning this, that learning just the nature of matter and particles without knowing fundamentally what forces might be and what particles are, and why strong and weak forces should hold something together. What are they? Why should the Higgs boson give mass to matter? What is happening? A lot of these questions are still dangling. There's no hard and fast answer to these questions. So I started, constantly asking these questions in an unorthodox way, even to my bosses, to the physicists, and really irritated some of them, because here I was, this very lowly undergraduate who's just gone on a simple internship and been given a very small task, like, study these photomultiplier tubes, which is one small segment of the whole cyclotron. And yet I was going to every professor and asking them fundamental questions, what are these quarks? How do you pronounce quarks? Is it quarks? Is it quarks?
Right.
What are they? And why should they comprise protons and neutrons? And what are these electrons? How do we know they're even there? If they're just a probability, then there's nothing that's actually existing, is there? And so there were these philosophical questions, but I noticed that every physicist was a super specialist in quite a narrow domain. And it was not trickling over to the rest. They weren't experts in the other field. But something like the cyclotron was such a large experiment. It actually involved particle physicists. It involved engineers, all kinds of, people who are just an expert in oscilloscopes and looking at certain sub-regimes and sub-areas. And yet the whole thing tied together. It seemed that there were just one or two people who seemed to know the macro phenomena of what was going on, what was even fundamentally being studied, why you're here. So if I asked my internship fellow interns and friends, actually they had no idea what the larger picture was. Just as I had no idea what the larger picture was. I sort of knew what to calculate in a narrow area, but I didn't know what that fed into. And internship after internship, whether it was in plasma physics the next year or wherever else, I felt that I was mastering a tiny area, and that itself took all my energy, involved a lot of mathematics at that level. It felt quite high level, and yet I was not getting the full picture. So I kept looking further and further, and I used the word indisciplined. So I was sort of zigzagging all over the place, Nisha. So I did an internship in a different field every year. So, the first year
Wow.
it was at Brookhaven National Lab. The following year it was at Princeton at the Plasma Physics Lab, trying to understand that. The following year, funnily enough, it was at Exxon, trying to understand polymers, yet another field, and then trying to understand, viscoelasticity. And that, of course, was at an oil company,
Yeah.
and they had an R&D wing, so it was quite a bit of physics there. And that led me to geophysics for 2 years, where I did my master's. And I felt I was previously happier doing maths, so I delved into maths, and that's what my doctorate is in applied mathematics and fluid flows. But I tried to time what I was doing in fluid flows across the board. So, of course, geophysics was about the oil industry. That's fluid, flowing through the cracks of the earth. I did my undergraduate on fluid dynamics and what they call boundary layer theory. And I explained the biology problem of blood flow.
Yeah.
But it was a very mathematical thesis. So that also was understanding fluids and understanding how flows occur, within compliant surfaces. And then, following that, I also did some viscoelasticity studies in Slovenia. So one thing led to the other in this very long-winded journey. But I'm grateful, again, tying back to your original question, I'm very grateful to Krishnaji for allowing me to stick to these questions regardless, and not search for them in a particular narrow domain, not just through physics, not just through mathematics, but the intrinsic value of the question. And if mathematics can give me an insight, or physics can give me an insight, well and good. But I'm not going to kind of only search for something through a particular lens.
Yes.
I know it's a very long-winded
but there
way
are
of answering your question, and I hope it hasn't taken too.
No. So what I would like to know from this is, so it's a very nice, interesting story, and I think one of the first observations I made is that yes, you were introduced to certain fundamental questions through your father, then through you were yourself directed to Jiddu Krishnamurtiji's works, but the drive in you was there. So because some people might be introduced to the question but might not feel that driven to pursue them. So in your case, something came to you that there is something to be understood about the world, and then you said, okay, it can be found in science and I'd like to find it. And then this whole thing of knowing your love for patterns, going from Princeton to Exxon to this and that, would you say then you were looking for some kind of a pattern in trying all these different things and say perhaps find an answer to whatever the question? Did you have a fundamental question, or was it like total curiosity driven search?
I think it's the latter. It was total curiosity-driven search, and it was hoping to stick to something enough in order to find some sub-question and then relate it to something else. But it was in a very, very broad sweep. It was really trying to understand fundamental physics, I suppose you can call it that, but also patterns. Patterns, for example, I had a greater leaning for through mathematics. So I was trying to bring in mathematics, bring in physics, and merge them and see them as one. And the more I tried to see just them as one, the more I realized, but why not big questions of philosophy as part of the soup? And the more I started looking at that, I said that, well, but everything else is related, So my quest was for actually really threading all kinds of fields into the realm of physics and mathematics. And I also found an avenue to do that while I was an undergraduate. I did not want to divorce the humanities from everything, because again, this comes to the personal level, but, my mother is just at the opposite end of the spectrum. So she used to teach Urdu Sufi poetry. And in that realm, in the realm of Sufi poetry, in the realm of Persian poetry, there's a lot of pattern in the Masnavis.
Right.
And my mother used to say, I think I'm doing just, my realm and my field is just the opposite of yours. And she and I, we would always examine or ask this question, that at the highest level is mathematics and physics the same as Urdu poetry?
Yeah.
So something as bizarre as this, that doesn't really come into standard physics at all, I found was not so bizarre. So if you really look at who were the ancient astronomers, mathematicians, and physicists, like Umar Khayyam, the Arabs, for example, they all tended to be poets. In fact, we know them very well as poets. Many of them were, like the father of medicine.
Yeah.
Yes. Of course, Umar Khayyam with the Al-Tusi for, medicine, mathematics, conics, whole realm.
Right.
So I said that, what was it? Did they just enjoy doing mathematics, but were also musicians, quite separate? Because we tend to separate everything into streams, right? So you are a maths person, so that's one realm, your maths and physics, yes, you can see the tie, even with the other sciences. But if you're a poet or a musician, you're seen to be, in a completely different direction. But all these mathematicians and scientists, very heavy duty scientists, really, at the realm, at the helm of all these fundamental questions, you can call them the giants on whom, the next generation of mathematics and physics came along. What were they, why were they poets, and these great poets, and what were they, and why did their masnavis have this beautiful rhythm and have this pattern? So yes, this quest for pattern, that was there across the board. And I really wanted to see it in the humanities. And perhaps we can discuss a little later how the humanities very luckily did pour in. And I could see, I see, it's not so unrelated.
Right.
And the more we understand the humanities, in fact, all scientists and physicists, I feel, to be very well educated in the humanities, because I feel they'll almost be better and more insightful physicists then, and vice versa. I really think that there is this interaction, and I might be saying something a little controversial, but I hope you'll forgive me.
No, but what you're saying, I read this book. I was reading this book called Holographic Universe by Michael Talbot, and in this he has quoted the author has quoted David Bohm quite often, and I also watched one of his videos, and he's also talking about the interconnectedness of things, just like you were, like. Although we ended on the topic of poets, but before that, you're talking about how things are kind of connected. The more you saw connections here, the more you saw connections in things outside. So here is a quote from this book, and this is the author, Mr. Talbot, writing. Indeed, Bohm believes that our almost universal tendency to fragment the world and ignore the dynamic interconnectedness of all things is responsible for many of our problems, not only in science, but in our lives and our society as well. For instance, we believe we can extract the valuable parts of the earth without affecting the whole. We believe it is possible to treat parts of our body and not be concerned with the whole. We believe we can deal with various problems in our society, such as crime, poverty, drug addiction, without addressing the problems in our society as a whole, and so on. So it is, am I right in saying that? Like, because he also saw that in physics, we are constantly dividing, even in the way we answer the questions that we ask, like some of these fundamental questions. So yeah, he also seems to think on similar lines, that things are connected together, right?
Oh yes, I mean, I'm not quoting myself as any expert here, but certainly David Bohm has also been a major influence, because his interest in connecting the whole, I think it came from insight. It wasn't just wanting to connect things just because you're looking for connections, but through insight, understanding that at a deeper, very fundamental level, everything is interconnected. Things that are unexplainable in physics, for example, that have been at the macro level tested, just kind of leave us quite bewildered. One such phenomena which I might not be able to technically explain very properly, properly in this, just quickly here, is say quantum entanglement.
Right.
So two particles,
Right.
after they've met, I'm putting it metaphorically,
Mm-hmm.
even after they're or nearly infinitely separated, somehow their properties become intertwined. They sort of remember each other. How does that happen? So and this is happening and tested at the macro scale.
Right.
So they get their properties in some sense get entangled despite infinite distance. So they're not actually. What does this mean? Infinite distance. It just means that their communication really cannot happen because it's happening in a way faster than the speed of light. They're as though they're one thing.
Right.
Although opposite phenomena might be happening, in terms of spin directions or whatever the physics manifestation is, but they fundamentally become intertwined. So is everything, therefore, connected, not just in terms of its twin entangled partner, but fundamentally all around? So that's a very big question to hold, which David Bohm mentioned. And when you mentioned Michael Talbot, thank you for giving us this quote from there. But David Bohm also talked of wholeness and something called implicate order.
Implicate order.
Yes, the order of the enfolded, as though something very fundamental about the nature of things is at a level that's hidden, and then it manifests itself. So the hidden is a kind of level of reality that that you can't quite see, but at a superficial level, it unfolds. So you can see its superficial manifestation. And by superficial, I don't mean, I actually mean its physical, outward manifestation. So there's an inner and there's an outer. And this is a very interesting phenomena. And I think the book that you mentioned is now by Michael Talbot. He probably also talks about the nature of the universe as such. So what is a hologram?
Yes.
A hologram is something that holds a lot of information in a 3D manner.
Right.
You see, so does something that's hidden hold a lot of information, and then the unfolded form then manifests parts of it. Yeah.
Amazing.
So these might not be the right analogies, but I'm going to try give it a shot anyway.
Sure.
But go out on a really still night and look at the stars. So I'm talking quite romantically here, because there's so much beauty involved in this. And on a very still night where, hopefully a pollution-free space, you'll be able to see all the stars and the beautiful night sky, practically all the visible universe, right?
Right.
And where do you see it? Apparently, it's held in the retina, right? So something very small, right, hidden, is actually holding something so large and so vast. So the entire universe, the visible universe, including the positioning of the stars, of the entire night sky, the nebula, the planets, anything and everything that's dotted in, including the dark space in between, which might contain black holes and everything, all of that is held in your retina, in your little old retina right here, something that is so tiny and so far away and so seemingly insignificant. If we look at the size of the earth, that's insignificant as when we're talking about these very vast cosmological scales. So the size of your retina is zero, really. So, but it's holding implicitly something so deep and so vast and so profound. Correct?
Yes.
So there's an enfolding and unfolding of order. Yeah.
And I want to share this with you. exactly on this thought. So remember, I earlier had shared this film, the name of this film with you earlier, A Wrinkle in Time. So in that, this concept, so the hero is an astrophysicist. He's a father, a husband, he has a daughter, and they're trying to impart, keep their daughter also open-minded and open to physics. And they tell her about something called, they tell her that it's something is enfolded does not mean it's gone. It's enfolded, not gone. And this kind of plays out
Right.
symbolically in his life, because he discovers a frequency which is love, and then he gets transported light years away from earth, right? And but his love for his daughter and his daughter's love for the father is not gone. It's right there somewhere. And then all these different forces come together. Now you can look at it from the point of view of science, like this is again metaphors from science kind of seeping into a work of art, of fiction. And when we people, the common people watch it, it still makes sense. Now, how are we connecting? Is it just the magic of the story, or it's unreal? No, maybe we're connecting on something more fundamental. We're responding to something. We're just not just seeing something new and being in awe of it, but
Beautiful.
perhaps connecting with something. Yeah,
And it's amazing what can come out of the response of something that's purely at an emotional or love level. Sometimes a work of literature can create a whole branch of a subject,
yeah,
of science. In
yeah,
fact, let's go back to the father of science, just illustrating this point.
yeah.
I suppose father of modern science and frequently thought to be so, Galileo Galilei.
Uh-huh.
He was inspired to invent and have insights on the whole of his science through a
Play.
work of literature.
Yeah.
Dante's,
Dante.
Dante's portrayal
Uh-huh.
of of hell
How?
in
Yes.
his Inferno. Yes, in his Inferno,
Uh-huh.
inspired him to actually develop a whole science, a whole, the whole
Wow.
of, of the kind of mathematics that he talks about in his lectures called Two New Sciences. It's
Wow.
he proves that hell of that proportion cannot hold. So, when hell is described so vividly by Dante, and then it's scaled up, he actually proves that that kind of scaling doesn't happen. So he develops these laws, these scaling laws of material, of matter, basically all matter. So it
Right.
doesn't scale linearly. That's what he says. So let's think of an example. So say you have a four-legged creature and you want to just scale it up in size.
Right.
Its body is going to be distorted. Have you ever wondered why an elephant, as gigantic and beautiful and stunning as it is kind of funny looking, right? It's got all these funny bulges. So when it's scaled up, it doesn't scale like a horse. It scales like a completely different animal because it's so much bigger. So those laws of physics, when you scale from something small to something big, it doesn't scale up linearly in terms of the matter, in terms of
So, what does
the
this say about
elasticity.
imagination? So, an artist imagining and having bounded by rhythm of his poetry, choice of words. There is
Yes.
discipline in that, and then there is a scientist who also has his imagination, which is also bound by its own reasoning and everything. So, what does this say about imagination for you?
Oh, this is such a beautiful question you're putting here. I mean, this is such a good example of where a work of literature inspires you to invent, what has been called modern science
Right.
at some level, and of course thereafter, Newton and other, and we're talking about kind of modern, I suppose, technological science. So what is it about the imagination that's tickled? Um, so you invent something which is quite the opposite of what you are witnessing on
Yeah.
or seeing for the first time. So it's like you've heard a piece of music
Yeah.
and you come home and you write a whole bunch of equations. How strange is that?
Yeah.
Completely inspired by that piece of music. And in fact, that used to be the case. I mean, the great tabla players of the past developed or understood the Fibonacci sequence from the tal of the tabla. Basically just answering that question: how many ways can you play the tabla beat if there's only a short beat and a long beat allowed? How many ways can they emerge? So your tabla raga or whatever it is called, it sort of sequence comes out in the form of the Fibonacci sequence.
Wow.
And Manjul Bhargava, who's a field medalist working at Princeton, he talks about it quite clearly. So if you want to find out, you can listen to one of his lectures online. Yes, and he talks about the nature of the beats of the tabla and how it kind of emerges as the literally as the Fibonacci sequence. Basically the number of ways in which the beats emerge. Yeah. So I'm not explaining it fully because we're not spending time on this, but I do mention it also in Reimagining Mathematics, for instance, in one of the chapters. So here's a clear link between music and mathematics, yeah, and a clear link also between poetry, the beats of poetry, and also mathematics, because it also follows the Fibonacci sequence. If you look at Pingala's poetry. So if you look at one thing, through imagination, even through love, as you say, in A Wrinkle of Time, and out pops something that's very, kind of hard science, mathematical, then what is going on? What is this peculiar marriage? And why this separation then? Why are we separating all these subjects as so different? And why are we saying only physics can answer these big questions? Why can't insight answer these big questions? What is insight even? So these other realms become much more important, other areas, of the humanities. I suppose it's categorized as the humanities, but it starts feeding in. So
yeah, and I knew when we will talk about Jiddu Krishnamurthy and Mr. David Bohm's name will also come. So I started watching some of their videos. And there is this one, which it's an interview of Mr. David Bohm from 1989. And he was visiting the Bohr Institute. And that's when the interview took place. So the interviewer, what he asked him was, if it's easy to understand for the scientists that he was delivering his lectures to, was it easy for them to understand the new perspectives that he was bringing in? This was the question. Yeah. And to which he said, I think scientists find it harder in some ways than other people because there is a strong commitment, perhaps even partly unconscious, to the old atomistic worldview. They've become so used to seeing that they don't want to change it. They feel uncomfortable about changing and they feel no reason to change. And many of them say, we are going so well now. Why should we change? In some sense, it looks as though we are doing very well. But if you look at the broader view, it looks very dangerous. So I hope it doesn't seem like a break from what we were talking, but I wanted to stay on understanding certain things about what Mr. Bohm is saying here. So why would you say that? And or rather, what are your thoughts on this distaste towards changing that some scientists have, and some scientists like Mr. Bohm don't seem to have it? They seem to be more open-minded. What's going on here?
Well, that's a very interesting question. I think historically there's been a distaste to any standard thought process, mainstream standard thought process, whether it's in science or any other realm, being challenged and particularly overturned. Most people don't want to change the status quo or say they've been they've been doing experiment after experiment that seems to work. You might also say, why rock the boat? I don't need anything else. But very often it's not rocking the boat. Whatever they've been doing in the past does not explain everything. Suddenly there'll be a new phenomena that completely overturns the original theory. then what? Sometimes it challenges you in such a way that something that you've been working on for years and years and years has to be re-looked very, very deeply. So being so open to that, to different ways of thinking, and also mathematically, which of course David Bohm does while he was working at Birkbeck College. It wasn't just theory. He had kind of mathematical, he was a very strong, very world-class mathematician. In fact, his initial book was on standard physics, the quantum theory book that he first wrote. But pushing the boundaries is something that's very important. And I think it's very important for real science and for real thinking. Let's not even call it real science. For real thinking, for real questing, for real understanding, and for seeking truth. You can't really be stuck in any region or regime or realm because that's where not just imagination, but a kind of flexibility is required. In fact, that's also encoded into science. Very often, theories are overturned and then put to test. The new theory is put to test, and then that becomes the standard. And then that is challenged, and that becomes the standard. So it's been moving from ancient times. What we used to believe in the past obviously had centuries and centuries of change. Earlier, you might be put to the stake or something, or burnt at the stake for your ideas. And now, metaphorically maybe, but nobody will attack you for your ideas, at least explicitly. But still, the hesitancy is there. So David Bohm is quite right. When you really challenge the way and the comfort zone, things become very uncomfortable. And especially, in standard physics as well, many physicists don't want to, ask philosophical questions as though it's the same thing. They sort of, shrug it off. But I think a very good education, a layer of philosophy, and understanding where these big questions came from, even understanding historically how physics was developed, right from Plato's thinking and times before that even, looking into ancient Indian thinking, all this, it should be part of the education, so that it's a journey that allows you to see how things were looked at quite differently. Maybe there was a historical moment in time where things kind of moved in one particular direction. Suddenly everything got placed on a grid, like Rene Descartes' Descartesian grid, coordinate system. But, we started measuring things as the world picture, but it wasn't always like that, So go back into the past to see how there were many other cultures approaching things. That is very important.
So one is getting a historical perspective on things. So, and if you, for once, if you remove this situation from science, this seems to be a human condition, meaning that it's not easy to give up on things that you've believed in. It's not easy to give up on your beliefs that you've held on for years, and that seems to be a part of the human condition. Now, but you seem to be someone who has been able to keep an open mind. If I'm not wrong in saying that. Now, can you tell me apart? We'll see now. Like apart from, like you've already suggested, like having a historical perspective on things gives you a sense of things having always changing. Something better takes over from what was before it and builds on it. So there is a transformation that's happening. It's in the nature of the subject that you're doing. What would you say are some of the other insights that some practical insights that you can have generally for people like me, like others, for whom it's difficult to break out of a certain box, a box in physics, a box in science and math, but generally in life? Has your approach to physics given you some insights on how to break free and how to keep an open mind?
Again, I don't want to trickle back into history, but I'm going to lean on a little bit of history here. Studying a bit of history from other cultures can sometimes help you break out of this, and I'll be very careful to lay that out. For example, one example that comes to mind is in Japan, during the Edo period or Edo period, suddenly there was a period where there was very little interaction with other cultures within Japan. So outsiders weren't really allowed in, and the Japanese weren't allowed out. So there was a very large span of time where the Japanese were within themselves,
Right.
and there was a huge chance for a lot of cultural enrichment happening. During this period, very oddly enough, a new type of mathematics called, let's call it sacred geometry, but temple mathematics, sacred mathematics developed. So it was completely a different way of thinking of mathematical problems compared to how, say, an ordinary person, say like me, studying, Western science and physics and mathematics would see, how we see geometry and mathematics and calculus, before that trigonometry, etc. We look at it in a particular way, but this, it may ultimately come to similar things, like ultimately lead to calculus in some way or the other, but the whole way of looking at it was completely different, and it was seen very spiritually, if I may say so.
Right.
So temple mathematics was that, it was like a little discovery, almost like a Pythagoras, during the Pythagoras era, similar things happen. And so it is so sacred. Say I discover certain fundamental features of a geometrical problem, I will take it to the temple. So that's such a strange but beautiful thing. So I'm holding it to such a high esteem that this beautiful solution is so sacred. I'm going to offer it to the gods. So that phenomena started taking place, and a new type of mathematics was being formed. You see, so if you look at the history of the Edo period, what does it tell us? It tells us that just be open-minded. A lot can happen where you least expect. Lots of insights can happen where you least expect. Example number 2 I shall give, and this might be more concretely understandable. Certain numbers were considered to be very, very important in the in the times of the Joseon era, if I'm saying it correctly, in South Korea. So I'm going to give just an example of a Joseon era, again historical setting in South Korea. During the Joseon era, there was a king called King Sejong, and he became quite obsessed with magic squares. So what are these magic squares? Basically, if you have literally a square which is cut up into little sub-squares, and you put numbers in there. Basically, if along the horizontal lines and the vertical lines, the diagonals, if the numbers that you put there add up to, say, 15 across the board, so across, down, diagonally, that's a 15 by 15 magic square. So the bigger your magic square, the more difficult it is to fill in the blanks, yeah? So I don't know how true this is, but I saw this in one of the Korean serials called Tree with Deep Roots, which talks about King Sejong and his obsession with the magic square of the Once he was able to solve it, he would understand something about creating the Korean alphabet. You see how seemingly unrelated they are. So you're filling up a mathematical problem. But what he was trying to do is he was trying to create the Hangul script, which is a very simplified kind of alphabet version of the, for the Korean language, so that people could learn how to read and write and not rely completely on the Chinese script and characters, which were too many for the common people. Right? So he was trying to create a script for the common people. And I think initially it had 28 alphabets, letters in the alphabet. And 28 is also a very interesting number. It's a perfect number. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 also adds to 28.
Wow.
And all the factors of 28 add up to 28. So
Wow.
it's a very interesting number. But he created initially this alphabet system, this Hangul script of 28 alphabets, but it was inspired through working out this magic square, which he spent many, many years on.
Right.
And exactly what the link is, I suppose we'll have to watch the serial Tree with Deep Roots on Netflix to fully understand what was going on. But coming back to this original question of, how are we able to bring this insight in?
Right.
Again, I think through history. And then suddenly you open your mind and you say a lot of very interesting things are going on in different ways. People actually think intrinsically very different.
Right.
In the realm of Vedic
Right.
mathematics, certainly, numbers are looked at completely different. We look from we look at numbers or add and subtract from one direction, and Vedic mathematics looks at it from a completely opposite direction and is faster because it uses some very unique tricks, etc. So just be open, not just numerically, but at all levels of physics. You never know what kind of insight you might get. So that's fundamentally my little 2 cents.
Right. And yeah, so moving on from this a little bit in a slightly different direction. So when we did our episode on maths, one of the things I asked you, and in the series as well, was why do people fear maths so much? I had a real, genuine, concrete personal experience to bank on, and a lot of people had shared similar experiences across the globe. And people had some interesting things to say. So now I started to wonder also, I had physics too in school, science in 11th and 12th. But somehow this fear of math was always, in some sense, bigger than the fear of physics or biology or chemistry. Am I the only one feeling this way, or have you felt it yourself, or had other people speak to you about this? And do you have any thoughts on it? Why it might be so if it is so?
Oh, yes. I mean, that fear of maths, I see it all around because, I'm not a practicing physicist or a scientist or a mathematician, although I've written my book on reimagining mathematics, more like, delving into these questions that we've addressed slightly here.
Yeah.
But I love teaching young students, and I taught at a Krishnamurti school for several years. And occasionally, even now, I teach Waldorf mathematics, really.
Okay.
And there is a kind of frozenness. In fact, I teach online some students who just absolutely hate mathematics, and just the idea of numbers just creates this kind of cold freeze, and they can't think at all. So why does this happen? Why do we see it so often? Right. Very often, we know that mathematics is an unpopular subject. I mean, among some people, it's very popular as well. So I'm not saying, everybody hates mathematics and science and engineering. Obviously not. There are millions who actually pursue that and like it as well. But the vast majority seem to just hate mathematics. And I really shouldn't kind of put the blame squarely on how it's taught and the classroom experience. But unfortunately, I will have to do that. I really just think it is the way it is taught, it is presented. The fear of mathematics is sort of almost planted in you from a very early age, because its joy and its beauty and its ease is not unfolded, shall we say, to use a word, to borrow David Bohm's terminology. So everything just seems so scary. By the time you finish just your basic operations of mathematics, addition, subtraction, multiplication, division, suddenly there's long division, there's fractions, and these fractions are doing funny things. And then in the mix of all of this, you bring in algebra and alphabets. Where did that come from? And then they seem to have a life of their own. Suddenly there's quadratic equations, and then trigonometry is where most of everything is lost. People just do not like it. Logarithms and trigonometry and forget calculus. By that time, everyone has decided to hate mathematics. Correct. So I really do feel that, first of all, imposing it in the style as a standard very basic structure that everyone is forced to do, that itself I think is problematic. That shouldn't be how mathematics is presented. And secondly, I feel there should be a much more natural way in which mathematics ought to be introduced. Children, really ought to play in nature as much as possible to see that mathematics is happening all around us. I mean, straight away they'll see that the flower petals that seem to know how to count. I mean, how does that happen? 5 petals, 8 petals, 13 petals. The way sunflower seeds are packed, that also seems to be, there seems to be so much order and pattern, even in chaos, even in a storm. So children ought to be kind of teased and exposed to all that and told that, just watch this, just observe it together. When you are throwing, just playing with the shuttlecock or playing badminton, that has so much physics in it. The parabolic motion of objects when you throw something towards someone, that is such a natural ball phenomena. Ball sports. Right. Everyone should ask these questions, and we don't as parents, we don't as teachers. It's as though the classroom is a standalone experience, and that I think is the mistake. Because suddenly, you have life, and then you're placed in this box. First of all, the look of classrooms is awful. You have this kind of square box. You stuff in as many people as possible, and the teacher just rattles on. And eventually, after this rattling on, sooner or later, you're going to lose the audience. So I really think the whole way in which science and mathematics and learning happens needs to be readdressed. With a lot more emphasis on inquiry, on silence, on observation, on even
ideas, concepts.
Why not introduce forest schools? Have these little safe spaces, but very natural spaces for children, where they come across things like what I've been mentioning, all these flowers with these flower petals, spirals, phenomena, round shapes. Where do these shapes naturally occur? And their nature. Right. Then the mathematics that you learn, in the way that you learn it, and also open-ended ways, will become much more friendly. There'll be a much more user-friendly version, shall we speak, of if that's one way of putting it,
right?
Of mathematics, of physics. And let not there be this, and let not there be this demarcation. The more humanities and the more poetry there is, who knows, the more insightful you'll be in physics and mathematics, as Galileo was.
Yeah.
And in Galileo's example, he was quite a late bloomer, so to speak. He did most of his mathematics and learned it at the age of 19. His father was a musician, so that's where that comes from. So in the past, if you could get so many mathematical insights from a different area or realm altogether, why not now? Why not revisit that and be very open,
very interesting,
and be very inclusive. Inclusive to new ideas.
Yeah. What would you say are some of the guiding principles of physics? If there is something like that, some principles that guide physicists, say fundamental principles, or that guide the subject. And what do you think? Do you think they have the potential to tell us something about what reality is? Those guiding principles.
Right. I suppose the guiding principles, I mean, there's how would you hold yourself to the discipline of physics?
Wow.
Of course, it's all within, you're sort of proceeding, and the only way I've held physics or known physics is in the standard way in which it was presented, Newtonian physics leading to higher sort of and different areas of physics. So what are the principles fundamentally that hold it together? Well, I suppose there are one or two principles. It seems nature is always conserving and minimizing. So that seems to be in the nature of energy, right? So for example, it's not completely random. Are you wearing a necklace, if I may ask?
No.
Yeah.
Yes,
so if you hold your chain at two ends and you roll a ball that you can, like a pearl or something that's threaded through, because of gravity, it's going to follow a certain quickest path, right? And what that path is a physics question. What shape the raindrop ultimately acquires is a physics question.
Wow.
It all seems to be a very conservative and a very clever way of packing or minimizing, very efficient, very energy minimizing. That seems to be a fundamental principle across the board. Yeah, that's one of them. I mean, there are many in different realms if you really go open into physics. But I'm just sticking to one here. And for example, you might also ask, is nature doing the same thing? Is nature, looking at packing problems? How do you pack something most efficiently in a small space? It seems yes, because you take your bees, and the beehive. Initially, I think the little bit of honey or nectar that it takes to its hive is spherical, presumably. But when it's creating the hive, it has this, six-sided, beautiful hexagon structure.
Yeah,
It's so mathematical, and that's in fact the answer to a question, to a physics question, to a mathematical question. What is the best way of packing? How much can you actually pack in? How much honey, for example, can you pack in the smallest space or in a given space? And it's actually a very complicated question. And it was only answered, I think, recent by comparative terms in like 1989 or so. It's called the honeycomb conjecture. Yeah, so you can look it up, the honeycomb conjecture. So it does address this, how do you pack something most efficiently? But again, it's looking at nature principles. Nature seems to be very protective of us, as though I'm now speaking metaphorically, as though you have what is the best way to conserve and to minimize, but also by minimizing, you're maximizing what you're giving, right? In a sense, you're finding the most efficient way to pack grains, for example, or seeds within your sunflower, for example. And it creates these beautiful patterns, and it's linked to the Fibonacci sequence, etc., etc. So that's also a good example of efficient packing. How sand also packs together small and large pebbles of sand, if I can call them pebbles, they're tiny ones. So the sand packing problem is also a very good question. Also how soap bubbles interact. I mean, so those, you can get into higher and higher and higher levels of complexity, right into chaos theory, etc. But it's fundamentally following certain very large, broad sweep kind of principles. And there are fundamental principles across the board, Energy seems not to disappear completely. So you say, things don't completely disappear.
And
you also...
Yeah, please go on.
Yeah,
please go on.
It doesn't, it's all conserved. Certainly in the standard way that we've been looking at physics, that may change. But so that's another area in which, something doesn't completely just vanish. Energy will exist in some form or the other. And also in the realm of order and disorder, it seems things started off with order and became more and more and more disordered. Brian Cox, if I'm quoting him correctly, in one of his videos, talks about how we pour milk into coffee. When we first pour it in, you have a layer of milk at the top. Seems quite ordered, So it's just a layer of milk, and there's hot coffee underneath it. And then you just leave it for a while, and it starts, if I may just coin a term, disordering. It becomes more and more disordered because all these little twirls start forming, and the milk kind of blends in. And with the passage of time, it'll all become kind of, your cup of coffee. But it goes through this very disordered these stages of getting from order to disorder. And it seems a lot of things, matter in general, and if you look at it right from the beginning, from the Big Bang, we seem to become more and more disordered. Certainly the world, it seems these days, is becoming more and more disordered, if I might speak to that kind of an analogy. So these seem to be some of the fundamental physics principles, Disha. If this is what you meant.
Yes, yes. Because if these have sustained, and these have sustained as ideas in physics, and these have seemed to sustain, as far as we've been able to see, these seem to sustain life as it is occurring today. Then, since we I think physicists look at nature to understand reality, perhaps. I don't know if that's even the right way to put it. But then these ideas are useful, because if you see arrangement also can be seen as organization. And generally these things are, when you have that in life, it's usually a good thing to have, right? Because you're also in line with how things occur in nature. Correct?
Correct. Right.
But the word consciousness, I'd heard it in a spiritual context, and maybe a religious context, but it also seems to have occupied a fairly large amount of space in physics. So what are your thoughts on, what have you been able to understand about this concept of consciousness?
Okay, maybe I can go back. I mean, this is a long time ago, decades ago, in fact, but I actually took a class at, during my undergraduate at Amherst College as, it was a class on kind of the realm between physics, computer science, mathematics, and biology, and asked questions about mind and consciousness. So I'm going back to that time, and it was presented by a physicist called Arthur Zanes at Amherst, and he actually, it was quite fashionable at that time to also ask these very connected questions, and try to connect various fields and into try to understanding the nature of consciousness, and asking what consciousness is, consciousness and the mind. And it was, I suppose, some of the lectures were from the perspective of computer science, like how do you know something is conscious, from an AI perspective, so we talked about the Turing machine and things like that. Then the biologists actually also came in and asked questions about where is the location of consciousness, certainly for human beings. Is it inside the brain? Is it outside the brain? If it's in the brain, where? Is it deep embedded inside the microtubules? I even heard this word for the first time, microtubules of the brain. And then we brought in David Bohm and Krishnamurti as well, delving into the realm of consciousness and mind, and what it meant. And I think my impression at the end of all that was that it's a huge, very important, but very open debate. And there were physicists like Roger Penrose and David Bohm, of course, really very deeply delving into the realm of what it means, what is consciousness, what first creates a kind of awareness or self-awareness that is not dependent on another observing it, so it can independently exist of its own accord. I say it poetically, full many a flower has bloomed unseen. So the flower that's blooming in the field, right? Is that reality? Yeah, is that still reality? And if that is reality, is it conscious? And what does consciousness mean in the larger scale of things? So it's a very open-ended question for me, Disha. I don't have a direct answer to it. There's many attempts, some through physics, some through, of course, in the realm of psychology and in the realm of computer science and artificial intelligence. People are asking these questions all the time. What makes something, even a machine, self-aware, aware of its own existence, What do these questions mean? Philosophically, also, it's a very complex and very deep term, right? Conscience. What does the summation of all knowledge? Is that the root word?
Yeah. With knowledge.
Yeah. With knowledge, yes, yeah. And what that means. And it's also, I think I have to be very careful because the word conscience, is it really about all knowledge? Because words very often, with the passage of time, become their exact opposite. So, for example, the words subjective and objective used to mean just the opposite of what it means now. So the original word, like subject is of the subject. So it's very particular, but now it means subjective, meaning, you're
anybody's
not
opinion,
precise.
whatever.
Yes. Yeah. So it's become its exact opposite. And objective was of the object. So it's very particular. So these two words, for example, have become the exact opposite. You see? So we have to be very careful with words and what they mean. Words like reality, words like consciousness. Maybe a better word is being and what that means. So we need to understand it at a philosophical level and then address that, I think, and then ask, what is, how does consciousness occur? David Bohm seems to think or say or hint, I think, in one of his talks, that it's not, we tend to think of a linear sense of time. Yeah, that earlier there was, things were very crude and there was matter. And at a certain point in time, things became conscious. But he feels consciousness is actually, it's kind of a mass phenomenon when there are, it's a collective. So when the collective is there is consciousness. So it's an occurrence that happens like that. It's not at a certain passage in time with a certain complexity. That, prehistoric animals were not conscious, but now we are conscious. Or prehistoric animals didn't have enough intelligence, but now, you have a much more complex being. You have intelligent man with a very complex brain that, of course, is looking at itself quite objectively. So where this consciousness arises, I mean, a good place to look at it would be to look at David Bohm's lectures and see what he has to say. Of course, there's, Jung as well, the psychologist. So we can delve into these areas, but the nature of consciousness when it comes to physics, it's a very big question. Yeah. And
it's called a hard question,
I can't
right?
wrap it. Yes, it's quite a hard question. I can't wrap it up except in the way that I've kind of presented it.
Sure. And okay, maybe this can be like the last question. Something that, your opinion on what you think is the goal of physics. I don't know if that's the best way to phrase it, but I hope I'm able to convey what I'm trying to ask. Like, what would you say it is?
Goal. Well, I suppose a goal could be really understanding maybe the nature of nature itself. I think that is the goal. I don't think much as it's a popular goal at the moment, unifying, the unified field theory, that's supposed to be one goal, kind of unifying all the forces of nature and finding a meeting point between the great chasm between gravitational physics and all that is before and quantum, etc. One goal could be to bridge all that, and there are many attempts like string theory that, and other mathematical theories, gauge theories that tend to do that. But I feel at a philosophical and fundamental level, it is to ask even simple questions like who we are, and I'm not trying to spring out of the earth into space exploration. No. Who we are, and let's just jump into, let's take the next rocket out. but who we are and what we are, and going back to the how and the why questions fundamentally, and keeping at them, this very deep inquiry. In fact, Krishnaji's inquiry seems to me to be a physics question. Inquire about everything, be very aware, observe constantly, um, you know, and that gives us huge insight. You can do it in, through hard mathematics if that's your thing, but you can even sit with the question, and any of us can. You can, and you're actually. So I hope that wraps it up.
Yeah. Thank you
way.
for that answer, Ashna, and thank you for coming again and doing this interview with me. Thank you so much. Thank you so much.
Thank you so much, Disha. It's been a very long evening, but really, really always lovely to talk to you, and so insightful. I think we went into so many different realms,
right,
and arenas together. Thank you again. Thank you to Tattva Deep for bringing us all together.
We hope this conversation helps the listeners see the tattva, or the true essence of physics, and the important role it plays in helping us understand the world we live in and appreciate the fundamental forces that lie underneath everything. It will be wonderful to know your thoughts on the interview, and if it inspired your worldview in any way. Thanks for being here. I will see you soon with another interesting mind demystifying another interesting topic. Until then, take care.